All right, guys, welcome back. Today we will be discussing optimization. Okay, so the big idea of optimization is really that you're trying to find the optimal scenario, the best case scenario for a situation. So you're going to be given several examples in which you're going to be asked to find like a maximum, like what will create the maximum profit, what would create the least amount of cost, or like what would create the biggest volume, or what will create the least amount of material used. So really the keywords here are really maximums and minimums. Those will be your optimal scenarios. Okay, so first let's discuss what steps should we be considering in order to be able to successfully optimize a problem using calculus. Okay, first you will want to identify what is known and what is unknown about the problem. Cool. Secondly, I recommend you make a sketch, although it's not necessary. I think it can be very helpful. Third, you need to figure out an equation of what needs to be optimized. So for example, if you wanted to maximize your profits, then you will need an equation for profit, right? If you want to minimize your cost, then you need an equation that minimizes your cost. Cool. All right. To minimize your cost, I'm sorry. All right. Number 4, sometimes you're going to need another equation because your equation that you're trying to optimize might have too many variables and you may not have enough information about those variables. So it could be helpful to find a secondary equation to help you reduce your equation that needs to be optimized into less variables. You might remember that if you've already tried optimization, there were some problems in which that tended to happen a little bit where you needed to reduce the amount of variables. So that's really what's happening here on optimization as well. Cool. Number 5 is, and it's very important because this is a real world application, you need to determine a feasible domain, right? So like as far as like for example, costs and profits, right? Like it doesn't make sense to have like, well, never mind, for profits you could have negatives, right? That means you have loss, but for costs you can't really have a negative. Cool. So that's what I mean by that. And then lastly, you're going to use your calculus knowledge, which is to find minimums and maximums. So in this case, using derivatives to figure out what is the best case scenario for the situation. Cool. So for our first example, here we go. We got a manufacturer that wants to design an open box having a square base and a surface area of 108 square inches. What dimensions will produce a box with a maximum volume? All right, so first things first, I'm going to look at what do I want to optimize? I want to maximize my volume. So, okay, first I'm going to write down what I do know. So I know that I have a surface area of 108 square inches. Cool. Secondly, I'm going to draw a diagram. That's really all I was given. So a diagram for this is we want a box that's a square base. I'm like, all right. So I'm going to do my best here. I'm not great at drawing. So here's my base. Here's my box. Let's see. Oh, that's terrible, but okay. You get the point. All right, so here's a box. I left it open, right? So the top, there's no material on it, but I do know that the base is supposed to be square. Okay, so if the base is supposed to be square, then that means this dimension and this dimension should be the same. So I'm gonna call those X. And it doesn't say anything about how tall it is, so I'm gonna call that H for height. Okay, so I've identified what I know. I've made a sketch. Now I need to figure out an equation that needs to be optimized. Well, in this case, what I need to optimize is the volume. So I need to figure out what would be the equation to find the volume of this box. Well, the volume of this box should equal to x times h. So that'll be x squared times h. Okay, so I want you to think about what I do know and what I don't know. All right, so what do I want to optimize? I want to optimize the volume. Okay. I know information about X, kind of, no, not really, right? So all I know is the surface area idea. So that means like, how does this come into play here? Well, let's discuss this. Well, if I wanted to find the surface area of this box, if I break this up into multiple faces, you would agree with me, hopefully, that there's a face here whose area would be X times H. And then there's a face here that would also be X times H. And then there's a face in this side and a face in the back that would also be X times H.
So that will be x times h times 4, because there's 4 of them. And in the bottom, I would have a base that is a square base. That should be x times x, so it's x squared. So then I could say that that's my surface area. My surface area would be x squared plus 4xh. So that's what I meant by a secondary equation. So let's see what I'm talking about. Right now, I have an equation that relates to volume, but there's 3 variables involved, so that might be difficult to deal with when we take a derivative. So what I'm thinking of doing is maybe I can utilize the fact that I know that the surface area is 108 to replace one of these variables. That's going to be my plan. So go ahead and delete this a little bit so I can have more room. So I know that my surface area is 108, which I can set equal to my surface area equation. I am noticing that I have an x squared here. So what I'm going to do with my plan is I'm going to solve for x squared here and then substitute it in there for the volume. So I'm going to say 108 minus 4 times x times h. Oh, no, actually, I don't like that. Here's what you got to keep in mind. I'm glad I kind of made that mistake. If I replace that in here, what I want you to notice is that's still going to leave me with a variable for volume. By substituting in there, there's still going to be an x and then there's still an h here. So the whole idea is you want to utilize this statement so that you can reduce it to only 2 variables if possible. So solving for x squared wasn't really a good idea. So I guess instead what I'm going to do is I'm going to solve for h. So that would mean I would take 108, I would subtract x squared, leaving me with 4xh. So I will divide everything by 4x. So then that goes away, which means h is equal to that. Now, as you can see, if I replace this h, everything here is an x, so now I just have x's and b. That's going to facilitate the calculus. Cool? So let's do that. Let's replace it. So the volume is equal to x squared times h will get replaced with this, so 108 minus, not 4x, sorry, minus x squared divided by 4x. All right. Now, if I were you, which I will do that right now, is I'm going to do a little bit of algebra to simplify this so that I can make the calculus easier. So first, I can say that this x squared can cancel one of these x's, so I'll be just x there. So then if I distribute this, this will be 108 x minus x cubed divided by 4, which again, I think I want to simplify my life a little bit more. I can factor out a 1/4, so I can have 1/4 and then have 108 x minus x cubed. So that is my volume equation, okay? So I'm like, all right, I've done pretty much all of the steps. I found a secondary equation. I used that secondary equation to help me simplify the optimization equation into 2 variables. So now let's talk about a feasible domain. Okay, based on what I have right now, if you think about it, the 2 variables that I have are v and x. So my domain is supposed to be dealing with the x's. So x is, what is x representing for this? X is representing the dimensions of the base, right? I want you to think this. According to the problem, I have this much material to utilize to make this box. So first, x is representing a dimension, which means x has to be greater than 0. X is impossible, right? I can't have a dimension for a box to be negative. But I also don't have a limited amount of material for me to say that x is just anything that's bigger than 0. So I gotta use a little bit of logic here. I know that the area of the base, so the area of the base is x squared. Now, if I were to not create any type of height at all, in other words, if I just make the base exactly all the material that I have, then I would have to say that 108 is equal to x squared. Again, that wouldn't help me make a box, but at least this is going to give me a feasible domain of what to do. Then I would know that x cannot be bigger than the square root of 108. So a feasible domain for this will tell me that x definitely has to be greater than 0, but it cannot be greater than the square root of 108. So when we get our answer should fall within these numbers. Cool? All right. So now, here is my volume equation. What am I being asked to do? I'm being asked to find a maximum volume. which means I need to find a maximum, which means I need to take the derivative of this equation in order for me to find a maximum. So what I'm gonna decide to do, since I have the variable v and I have the variable x, I'm gonna decide to take the derivative with respect to x. So what that would do is that would say the derivative of volume with respect to x, that would be dv over dx, is equal to, all right, this is just a constant multiple, so I can leave the 1/4 alone, and then multiply by the derivative of this. I decided to take the derivative with respect to x since all of this are x's. So the derivative of 108x is 108, and the derivative of x cubed would be, in this case, minus 3x squared. Okay? Now, in order for me to maximize something, remember from previous chapters, I will need to figure out critical numbers, which is where your slope is equal to 0. So I need to figure out where is this equal to 0, okay? This 1/4's gone, I can multiply it out, and then I can add 3 squared, so that will give me, let me go here, 108 is equal to 3x squared. Divide both sides by 3, okay? So 108 divided by 3, let's see, what does that give me? 108 divided by 3, so 318, that would be 36. So I'm sorry, that's gonna be x squared. Taking the square root of that will give me a 6. Okay, and that is the only value that produces a derivative of 0. Okay, now here is where now I make a decision of how will I optimize this. And really I have 2 options, guys. Okay, if you refer back to this very famous theorem called extreme value theorem, it states that if you have a function that is continuous on a closed interval, you are guaranteed to have an absolute max and an absolute min. Now, what does that mean? This volume equation, which I have here, it's a function that's continuous. This domain allows me to close it out, right? So now I have a continuous function on a closed interval. That means I definitely have an absolute max and an absolute min. So that's what I'm gonna do. I'm gonna do something called the candidate's test. You remember, the candidate's test is you create a table of values, okay? So in this case, would be x values, and your candidates are supposed to be your endpoints. So in this case, one of my candidates is 0. The other candidate is the square root of 108. And also supposed to be any places where your slope is equal to 0, which in this case, the only place where its slope is equal to 0 happens to be at 6. Okay? So now, I'm gonna perform a candidate's test, and to remember, all you gotta do is take your x values that you found, your candidates, and go back into your volume equation. Now, I'm not gonna go back into this equation because it has h's in it, and all I have is x's. I'm actually gonna utilize the volume equation that we came up with right here. Okay? Because it only has x's. All right, so plugging in the 0. 0 minus 0 before is 0. Well, that makes sense, guys. If my dimensions are 0, then that means I'm not even creating a box. Okay. Dimension number 2 is using the square root of 108. Okay. So that will be 108 times the square root of 108. All right, so that looks a little interesting. So 108 times the square root of 108 minus the square root of 108 cubed divided by 4. All right. I'm going to utilize a calculator to figure that out. So let me go ahead and grab one real quick. Okay, so let's see what I got. Let me use my calculator. So I have 108 times the square root of 108 minus the square root of 108 to the power of 3. Dividing it by 4, which, oh my god, I just realized that. That's the same, that's gonna give me 0. So I don't even need to do an estimate. Wow, brain fart, sorry, think about it. Square root of 108 cubed is square root of 108 times square root of 108 times square root of 108. 2 of those make 108, and then it leaves you with 1 square root of 108, canceling them out, okay? Which, think of the situation, oh my god, I can't believe I didn't realize that. Remember we talked about earlier how I came up with this 108? That would mean I would have like the entire base, I use the entire material, which would mean I would have no height. And if I don't have any height, I don't have any volume, okay? Now, that's 6. Well, let's see what happens. So if I plug in 6, then I would have 108 times 6 minus 6 to the power of 3, and then all of that divided by 4. Cool? All right, so see what that gives us. So 108 times 6 minus 6 to the power of 3, and dividing all that 4 gives me a 108. Okay, so now by the candidate's test, these two values produce what we would call, in this case, the absolute minimum, which makes sense for this problem, guys. If I don't even make a box, then the absolutely lowest volume that I can create would be a volume of 0. And by the candidate's test, now I figured out that if my dimension for x is 6, then I would create a maximum volume for this box to be of 108. So now I gotta go back and answer the question, okay? So I need the dimensions. So now I know that the max volume, in this case, would be 108, and it's a volume, so it would be cubic inches. And the dimensions that would create that would be, if x is equal to 6, but it's asking for the dimensions, so it has to be a 6 by 6, and now I need to figure out what h is. Well, let's figure this out. Remember, we had solved for h in a statement right here. Cool. We had divided this out and we had said h is equal to all of that, right? So in this case, all I would have to do is plug in 6, right? So 108 minus 36 divided by 24, essentially. So the height would be 3, according to my calculator. So the dimensions, which is what they were asking me for, would have to be a 6 by 6 by 3 inch open box, and it would create a maximum volume of 108 cubic inches. Cool? So, to summarize, let's make sure we really understood what happened. So let's do a quick walkthrough of what we had to do, right? Remember, we identified what was known, what was unknown, we made a sketch. But the most important steps for this problem was figuring out the two equations necessary to do this. Always try to reduce your equation that's going to be optimized into two variables, because it makes the derivatives a lot easier. And that's what your second equation is used for. Cool. Once you do that, guys, simplify your equation into two variables, find the derivative, find your critical numbers, and utilize a candidate's test. But in order for you to perform the candidate's test, remember, you have to find the domain, right? So that you can have endpoints, so that you know what are the endpoints to utilize on your candidate's test. Cool. Once you find your candidate's test, compare all the y values. The lowest will be your absolute minimum, the highest will be your absolute maximum, which, depending on what the problem is about, then you can make your decision based on whatever is your highest and whatever is your lowest. Okay? All right, so we're gonna try one more problem on this video, and then I will make a follow-up video in which I try a little bit more intricate problems, just to make sure that you really understood the topic, okay? So give me a minute, I'll erase all this, and then we'll try a new one. Okay, I'm back. So here's your second example for today. So I'm told that I have 4 feet of wire, and I need to use that wire to form a square and a circle. Okay. How much wire should I be using for the square and the circle to enclose the maximum amount of area? All right, so I'm gonna draw an image real quick and label some things. So obviously a square, we have a square. I'm gonna give it some dimensions. I'm just gonna call it x by x. And then I have a circle. I know the dimensions of the circle. I'm just gonna call it r for radius. Okay, so here's what I need to maximize. I need an equation that maximizes area. Well, I need to know that area in this case should equal to the area of the circle, which is x times x, so x squared, plus the area of a circle, which in this case is pi r squared. All right. So what I'm noticing about this equation, just like I did for the first problem, is I have 3 variables. So to facilitate this, it would be helpful if I can find a second equation to make this into just 2 variables. Well, based on what I was given, I know that I have 4 feet to make the entire square and the circle. So to make them, that would be like the perimeter and the circumference of this. So I can say that the total amount of wire that I have, which is 4, should come from the perimeter, which according to the dimensions, it will be x plus x plus x plus x, so 4x, plus the circumference of the circle, which is 2 pi r. Okay, so what I'm going to decide to do is I think I'm going to solve for r here and substitute it for r in here. So go ahead and do that. So it'll be 4 minus 4x divided by 2 pi is equal to r. Facilitate my algebra a little bit. I can pull out a 4 and I can pull out a 2 from the bottom. So then if I do that, that will leave me with 1 minus x over pi is equal to r. So 4 divided by 2 is just 2. So I'll utilize that data over here. So it'll be a is equal to x squared plus pi times, 4 divided by 2 is 2. And then I have 1 minus x divided by pi, and then all of that is supposed to be squared. Cool. As you can see now, it's only 2 variables. I'm gonna do a little bit of algebra, clean this up so I can then determine what's a feasible domain and then do a Candace test, okay? So I'm gonna distribute out that squared. So 2 squared gives me a 4, so it'll be 4. And then the top will be 1 minus x squared over basically pi squared. Let's keep cleaning this up. This gives me x squared plus this pi can cancel with one of those pi's. So then I can say I have 4 over pi times 1 minus x squared. And I think I'm okay with that with what I have. Okay, all right, now I need a candidate's test, right? Right now I have x's and a's, right? So that means I need a candidate's test. Let me go over here in which I have x's and a's. Now let's go back to what is x representing. So if I'm going back to this, x is representing actually the sides of the square. So let's think visibly what could happen, okay? I have 4 feet of wire, right? Which would mean if I let x equal to 1, then that'll be 1 plus 1 plus 1 plus 1, which would actually create just a square, not a circle. So I guess the highest or the biggest amount I can use for x is 1, and I guess the least amount of it would be 0, and that's if I utilize the entire wire for the circle, then I wouldn't have a square, I would just have a circle. So I guess my domain physically for this would be x cannot be greater than 1, but it definitely has to be bigger than 0. That way I can actually make both a square and a circle. So that's important to know. So that means this is actually going to be relatively small dimensions for the square. Okay, so 2 of my candidates are going to be 0 and 1, which I can go ahead and figure this out, right? Actually, like these 2 numbers out now, and then I'll come back. So let me come back. Let's figure out any values where I can get this equal to 0. Since this is all x's and this is a's, I'm going to take the derivative with respect to x. So that means the change in a over the change in x is equal to derivative of x squared is just 2x with respect to x, right? This is just a constant, so I'm going to leave that constant alone, so that'll be 4 over pi. This is a chain rule, so by the chain rule, I would have a 2 in the front, 1 minus x, the power goes down to a 1, the derivative of 1 minus x would be negative 1. So if I clean that up a little bit, so that would be the change in x over the change in a over change in x, I'm sorry, is equal to 2x. 4 times 2 times negative 1, so I'll be negative, so minus 8 over pi, and then I have this 1 minus x. Okay? I just need to figure out where this is equal to 0. Okay, so what I'm going to do is actually do a little bit more distribution. So I'm going to do 2x minus, if I distribute that, that will be 8 over pi, and then negative times negative would actually give me a plus, and that will be 8 over pi x. Cool. I need to figure out where this is equal to 0. So I should be able to combine this 2 and then bring this over. So I'm going to factor out an x from this 2. So let me go here. I'm going to factor out an x. If I factor out an x, then I'm left with a 2. And I'm left with a plus 8 over pi. I'm going to bring this over here by addition. So it'll be 8 over pi. To get x by itself, I would have to say x is equal to 8 over pi divided by 2 plus 8 over pi. All right, if I do this by hand, I need a common denominator, so I can put this pi and then over pi, so I'll be 2 pi over pi. So it will allow me to combine these two things, so I'll be 8 over pi over 2 pi plus 8 divided by pi. By keep change flip, by dividing these two fractions, I can cancel out the pi's, which leaves me with 8 over 2 pi plus 8. I am noticing that everything here is divisible by 2, so I can say 4 over pi plus 4. Okay, so I'm going to clean that up, see what that gets me using the calculator, because I have no idea what that is. So I got 4 divided by pi plus 4. So this is approximately 0.56, which definitely does fall within here. So what I'm going to do is I'm just going to use the exact value here and put it 4 over 4 plus pi. Okay. All right. So remember, now that you have all your candidates, because that is the only location where the derivative is equal to 0, I need to put my candidates into my area statement. Remember, my area statement is right here. Okay. So my area statement is right there. I just got to plug in those x values. Cool. So if I plug in the x values, okay, 0 squared is 0. Okay. 1 minus 0 is 1. 1 squared is 1. 1 times 4 over pi is 1. I'm sorry, 1 times 4 over pi is 4 over pi plus 0, so it's 4 over pi for 0. Alright. If I plug in the 1 minus the 1 will get 0, so this entire gets zeroed out, but the 1 squared will give me 1, so that will give me a 1 here. And now this one is where I will use the calculator because this is not a nice number, so give me a second. So I got plus 4 over pi times 1 minus that quantity squared make sure I'm doing this right. Sorry. What I got? 4 over 4 plus pi. Sorry, I pressed the wrong button, got the wrong answer. Apologize. Give me a second. 4 over pi times 1 minus 4 over 4 plus pi. And then all that quantity gets squared. And it got me about 0.56. Okay, so now let's do what let me figure out what 4 divided by pi is. That's gonna be more than 1 though, so that's a little bit like 1.27. Okay, so then looking at this data, I am looking for what would produce, how much wire should be used for each the square in the circle to produce a maximum area. So the maximum area looking at this candidate gets produced when I utilize 0 on the x. Cool. That would be the maximum area that I would create. So if I get 0 on the x, then that would mean that all the wire to maximize the area, all the wire would have to be used on the circle. That's interesting. Cool. So yeah, according to like the mathematics here, I'm making sure because I'm like, whoa, what happened? So definitely, in order for me to maximize area, I will need to use the entire wire on the circle. So that means, really, I mean, I can write that answer down, but according to this, I shouldn't have any dimensions. Cool. But just reading the question, making sure, let me double check how much wire should be used for the square and the circle to enclose. So yeah, so for a moment I was like, wait a second, what's going on? The question never said anything about that I have to make a circle and a square. It just says that if I were to, right, what could happen? I could make them, right? But to maximize the area, which is all they want, nothing will be utilized for the square. The entire thing, wire should be utilized for the circle. Cool. which would mean then if I do that, then remember your equation, where is that at? For the circumference of a circle, we know that circumference of a circle is 2 pi r. We now know that we have to utilize the entire wire for the circle, so that means this 4 is equal to 2 pi r. So I mean 4 over 2 pi is equal to r. So in other words, I have to create a circle whose radius is 2 over pi and then feet. That would be the dimensions of the circle, and x would have to be 0. So that's this problem. Sorry, I'm a little like, it was kind of a little weird of a problem. I got thrown off a little bit. I should practice these problems before I make the videos. But anyways, all right, so there you go. 2 examples for optimization. Like I said, I'll make a follow-up video. I'm not sure when, so give me some time, in which I'll work a little bit more of these optimization problems to provide you with more examples and more practice. Cool? Well, anyways, thanks for watching, and we'll see you next time.